All right, here we go. Hi y'all. I am doing some examples of some problems, working out the math here for you. So hopefully you should have gotten all the most of the concepts of 1D kinematics from our class on Tuesday. This is just as a supplemental, with just a little math working out. A couple of the problems are relatively simple, but some of them have some additional little ideas and things to go from there. Okay, let's get to it. All right, so our first problem here, um, you accelerate from 0 meters per second at 3 meters per second squared until you've traveled 30 meters. You then decelerate at 2 meters per second squared until you come to a stop. How long does your trip take? Okay, so one of the things we talked about is that all our equations only work when the acceleration is constant. And this one, obviously, the acceleration is changing. You got 3 meters per second squared and 2 meters per second squared. Um, and one of them is acceleration, one of them is deceleration. So what does that change? And the answer is that it changes it a bit in the sense that we can't solve the whole problem at once because we have two different accelerations. But the acceleration is constant, 3 meters per second squared, for a while, for the first 30 meters. Then 2 meters per second squared, it's constant until it comes to a stop. So we can just do it as two different problems, essentially. So we've got this first part, the acceleration, right? What we know is we know that v initial equals 0. Acceleration is 3. And change in x is 30. Right? And then for the deceleration part, we know that acceleration, if it's deceleration, we'll say it's -2, right? Because I think we're assuming at this point that the vehicle is, the initial acceleration is positive, so the second acceleration should be negative. And because it's coming to a stop, right, v final equals 0. But so far, that's all we know. But let's go back to this first part, this acceleration here. So I want to find time, right? So if I have those three values and I want to find time, the best equation is change in x equals v initial times time plus 1/2 at squared, right? This is 30 equals 0 plus 1/2 times 3 times time squared. Okay, this becomes 20 equals t squared. And if you do the math for that, the square root of 20 is, the square root of 20 is 4.47 seconds. So that's the time for the first part. But we still have this, and you get the time for this part. So here's the second thing we have to figure out. We need to know time. In order to get time, we need to either know change in x or v initial. We have the one of those two. And it turns out the one we can get is we can get v initial. And the reason we can get v initial is because the initial velocity of your slowing down is actually the final velocity over here. So I can solve for v final of the acceleration part, right? Do it this way, we get v final equals 3 times 4.47, and that gives us 13.4 meters per second, and that becomes our initial velocity. Again, it's because final velocity is at the end of a time segment, right? So we're dividing this into two time segments, but the end of the first time segment is the beginning of the next time segment. So this should be the final velocity of that moment. The moment of the velocity at the end of that time segment is the start of the velocity of the second time segment. Comes 13.4. And now we have three pieces of information, which means we can find time, right? Again, we can use v final equals v initial plus at. 0 equals 13.4 minus 2t. T equals 6.7 seconds. So the total answer is just going to be those two added together, and it should come out to 10.11.17 seconds. All right? Okay. Moving on to our second problem. Okay, so we've got a rocket. Now, I'm always curious what kids like watch rocket launch and everything like that. So when a rocket goes up, when you fire into space, there's the first stage booster that goes up for a while, and then it falls off, and the second stage ignites and it goes further. So in this case, we're tracking the first stage. That's the engine on the bottom of the rocket that's going to fire first. Then it gets a certain side up. It's going to fall off so that the upper part doesn't have its weight. Okay, so if I want to draw the trajectory of this, right? So the engine is here, right? 300 meters up in the air. The engine's here. And the rocket's like, up here. Right? Let's give it a little peek here. All right, and this part right here is going to fall. But one thing we should think about is that this is moving at the time, right? In fact, it's moving at the same velocity as the upper part, the second stage, and the rest of the rocket. So it's going to keep going upward. Okay, this is, in this case, this is a perfect example, but anytime you have an object that's moving, and if it disconnects from another object or drops an object, you get what's called an inherited velocity, right? So a better example of that would be like if you're in an air balloon. So your hot air balloon, you're drifting up, and you drop an object, okay? The object's initial velocity is not zero. The object's initial velocity is the velocity of the air balloon. When you say dropping means you're not giving it any velocity other than the velocity that you have, right? So you drop an object out of a car, or you, like say you're biking, you drop an object, it keeps moving forward. Now air resistance makes it slow down a little bit, but it keeps moving forward. It doesn't just fall straight down and stop. Try it sometimes. If you're just walking, walk across the room and drop a ball. It doesn't drop straight down. It goes a little bit forward. So same thing's happening here. We're going to get a continued movement of this object upward, and then it's going to come all the way back down. So I want to find what the maximum height of this stage is. Now, this is an interesting problem because we actually don't know, we only know the velocity at one place. We don't know what it is here, and we don't know what the velocity is here. But the only place we actually know the velocity is this point right here. Right? The velocity is 0 at maximum height. Right? It's not going up anymore, and it's just about to start going down, so velocity is 0. So we actually want to split this problem into multiple pieces. There's the overall, there's the up part, and I call it the down part. And actually, turns out we don't really have to do anything with the down part here, but in theory we could. So thinking about the overall part, we know that the change in x is negative 300 meters. It doesn't matter that it goes up. Remember, displacement, change in x is where does it start here to where does it finish? And it goes down 300 meters. The acceleration is negative 9.8. And we know the time is 16 seconds. For the up part, we know that the final velocity is 0, right? Because it's going up until it reaches that peak. And for the down part, the initial is 0. And we also still know that the acceleration is negative 9.8 for both up and down. Okay. All right, so what do we do with this? I want to find this point right here. And the way I need to do that is I need to find this distance. This is what I'm looking for. If I can find that, I just add 300, or I guess I could find this whole distance here. Either one of those. Now notice those are only related to either this right here, this is the change in x for up, and this is the change in x for down. Okay, so I need to find this or this, but I only have two pieces of information. So how can I get a third piece of information for up or down? Well, one thing I can do is I can find v initial for overall, because the initial velocity for the up part, for the overall part, is the velocity happening right here, right? And that's also the v initial for the upward part of the way it travels. So change in x, v initial times time plus 1/2 at squared, and negative 300 equals v initial times 16 minus 4.9 times 16 squared. Okay, you plug that into a calculator and you should get that v initial equals 59.6 meters per second. So now I know that v initial here is 59.6. So now I can find change in x, right? V final squared equals v initial squared plus 2a change in x. We got 0 equals 59.6 squared plus, well, I guess it's minus actually, minus 19.6 times x. Turns out x here is 181 meters, which means that the total height equals 481 meters, right? Okay, so let's take a little, so that's the answer to that question, but we're gonna ask a little bit more, okay? I'm gonna ask one more question. All right, let's mark that off again. What is the impact velocity? What is the velocity right at the very bottom? A lot of ways you can solve that now. Easiest is probably just to do the downward part. Actually, there's probably like a bunch of different easy ways to do it. Let's do the downward part. Okay. So we've got. No, let's do overall. I take it back. We'll do overall. So v final squared was v initial squared plus 2a change in x, right? So this is v final squared equals 59.6 squared plus, again, that's going to be minus 19.6 times negative 300, right? Because it is going down, so those two negatives, you have to make sure you get them right, because they'll become positive. And this, it turns out, leads us to v final equals 97.1 meters per second, if you put it into your calculator. This is wrong. So why is this wrong? This is wrong because your calculator, when you take a square root of something, always tells you the positive root. But we know, based on everything else we've done this, that down is negative. We also know that when an object hits the ground, down is negative, right? It's going down, so it should be negative. So really, it's this negative value of that. So the one thing you gotta be careful when you're taking the square root of something, all right, to make sure that you pick the positive or negative based on what you know is happening. Okay. All right, two more here. Let's do this one here. It's a pretty straightforward one, but it's sort of a math thing, not a physics thing. I would say more of. But basically, we're talking about a situation where you go at a certain velocity for a certain period, like constant or average, and you go for a different velocity for a later period. Okay, and it's important that we're talking about averages here because what you're going to find is that you can't average averages. So you want to go you want your total to be 100 kilometers an hour, right? So if we're looking at this as like your overall, you might say it's 200 kilometers, 100 kilometers per hour, right? The first part is 60 kilometers, 80 kilometers per hour. And the second part is, I guess we know it's 140 kilometers. The question is, what's this? Well, the easy answer is like, well, I need a 100 kilometer average, so I would average 80 in this, and I would say it's got to be 120, right? Right, that 100 kilometers per hour is the average of these two values. Makes sense, right? But here's the thing, these are both averages. This is an average velocity, and this is an average velocity. Turns out you should never average averages. It doesn't work out mathematically, and I'll show you why right here. So right here, we got this, 200 kilometers, 100 kilometers an hour. This is going to be 2 hours long. Here, 60 kilometers, 80 kilometers an hour, that's 0.75 hours. And how long does this have to be? This has to be a total of 2 hours, right? So it has to be 2 hours minus 1.75 hours, so we get 1.25 hours. Now, what's the average velocity here? It's going to be 140 over 1.25. That is not 120. It's 112 meters per, or kilometers per hour. Okay, so we have to be a little bit careful about when we're averaging averages. All right, just one small thing. Okay. All right, last problem here. This one's a tough one. I might need an extra page for this one here, guys. We'll see. All right, so we've got you do two tests in your car. Okay, basically you're driving at a certain speed, and then someone flashes a light, I don't know, the stoplight or something like that, and it measures how long it takes, how far you go before you stop. Now that consists of two parts. In the first part, you have a reaction time, right? You don't hit the brake instantly. There's, I don't know, typical reaction time for a human is no better than 0.1 seconds if they're really paying attention. For if you're like not 100% focused, like all the way there, tends to be around 0.5, 0.7, 0.4 seconds. So there's that part, and then you start braking and you come to and you slow down. So there's those two parts. Okay. So in the first test we do this, you're traveling at 30 meters per second, you stop in a total of 60 meters. Another 20 meters per second, you stop in 30 meters. And I want to know what is the reaction time and what is the car's maximum deceleration. This is tricky because it's not obvious how you get there until you sort of get into it. The math turns out it works out really nicely, but the path there is a little bit complex. So first off, let's start with the idea of what is this 60 meters? Like this 60 meters. So 60 meters is equal to change in x while you're reacting, so I'll call it reacting time, right? Plus the change in x while you're braking. And actually this is really both, this is the trial one, so it's one for both of those. And we have 30 is equal to change in x reaction times 2 plus change in x braking 2. That doesn't seem that helpful to start. But we actually know what this is. This we can say change in x reaction time is equal to the velocity times your reaction time, right? And the change in x of the braking, right? So for the braking part, we know that the initial braking is 30, the final braking is 0, and the acceleration of braking is just a variable. So we can find change in x braking. So change in x braking is just going to be, sorry, we can't go directly there. My bad. But if we have those three variables, let's say I want to find change in x braking in terms of these ones, I could use v final braking squared equals v initial braking squared plus 2 braking, change in x braking. This is 0, 900 plus 2a change in x braking. And I can solve for change in x, the distance you go, the displacement of braking, right? So it becomes negative 900 over 2a. I can do the same thing here, right? So reaction 2 is 20 times t reaction. Initial velocity of braking is 20. The final braking is 0. A braking is still A braking, so we can get the same idea. It's still going to be V final braking squared equals V initial braking squared plus 2 acceleration braking times change in x braking. This is still 0 equals 400, so that's 20 squared plus 2 times A braking change in x braking, right? And this gives me negative 400 over 2a braking equals change in x braking. All right, so with all of that set up, and again, this is just plugging things in that we know. We go back to these first two equations. This becomes, we now have 60 equals 30t minus 900 over TA, 2a. And we have 30 equals 20t minus 400 over 2a. Right? So I got two equations, and all of a sudden I have two unknowns only. So, easy way to do this is actually to subtract. So I'm actually going to multiply this one by 1.5. So this becomes 45 equals 30b minus 600 over 2a. And I can then add these two together, or subtract these two, this one and this one. So I get 15. Oops, I made a mistake there. This is not a b. This should be a t. So 15, the t's cancel out. I'm now adding this because I'm subtracting it, so it becomes 300 over 2a minus 300 over 2a. And so a equals, when we solve that out, negative 10. And then I can plug that back into this one, say, okay, and you're going to get that the time is 0.5 seconds. Okay, so we knew neither the acceleration or the time for this, but we were able to find both the reaction time and maximum acceleration, deceleration of the car by doing two different trials, and even though we had two unknowns. All right, so that's a pretty complicated one. That's one of the most complicated problems I think you can do with this. So we're going to stop it there. Hopefully that gives you some idea of just some of the math and working through. And yeah, all right.